Alright, this is the last one we're going to look at from the 2017 exam. This is number 6. Last one of the week, I believe, for you AP kiddos. So 2017 number 6, the national average on this question was 1.1 out of 4, which is a little bit frightening. And so a couple topics we need to make sure we're comfortable with. So here we go. 6A, this says, answer the following questions about magnesium hydroxide. The value of the KSP for magnesium hydroxide is 1.8 times 10 to the negative 11th. So KSP, we're talking about solubility equilibrium. This says, calculate the number of grams of magnesium hydroxide that's dissolved in 100 mils of saturated solution. So you've got a KSP. We're trying to figure out what is the solubility of this. If we can figure out the solubility of that, we'll know how many moles of that per liter. We know how many milliliters we've got of it. We can go grams to moles, and so it's a little conversion factor after the KSP problem. So here we go, KSP equals, when we're talking about magnesium hydroxide, it's the concentration of magnesium times the concentration of the hydroxide ions. Its products raise their coefficients, right? So that should be squared there. So this stems from this dissociation of magnesium hydroxide. So we break this into magnesium ions and into 2 of those hydroxide ions. So when we look at this, Rice table wise, our initials of these guys when you drop magnesium hydroxide in water are zeros. You have to gain on that side because there's zeros. So we're gaining X here and we're gaining 2X for the hydroxide. And so when we go to plug our values in to the KSP reaction, we got an X and a 2X here. So KSP they gave us 1.8 times 10 to the negative 11th. What does that mean? Very little of this dissolves is what that means. Equals, let's put a little arrow there, equals the magnesium would be X at equilibrium times the hydroxide. That would be 2X from the Rice table at equilibrium. Don't forget to square it in that expression. And so 1.8 times 10 to the negative 11th is going to equal 4x cubed. Divide by 4, take the cube root of it, and you get x equals 1.65 times 10 to the negative 4th. Define it, right? What is x? X is the molarity. That's the molarity of the magnesium hydroxide that dissolves in solution. They don't want molarity here. They want how many grams of magnesium hydroxide would be dissolved. And so if I'm trying to convert molarity to something else, the sooner you can take that 1.65 times 10 to the negative 4th and make it molarity moles per liter, the better off your life will be. That's moles per 1 liter. We need to get grams out of it. So we've got to get rid of our liters. We don't want that liter unit. So how many liters are we dealing with here in this problem? It's right there. It's dissolved in 100 milliliters. So we don't have a full liter. We only have 0.1 liters. And so 1.65 times 10 negative 4th times 0.1, we get 1.65 times 10 to the negative 5th. What's left unit-wise? Just moles. That's moles of the magnesium hydroxide. That's how many moles dissolved in 0.1 liters. They want to know how many grams dissolved in 0.1 liters, and so we take that moles and we go moles 2 grams of magnesium hydroxide. Those sweet angels gave us the molar mass here. We're fuzzy. 58.32 grams. So we have 58.32 grams per 1 mole. And that will tell us how many grams dissolved. I got very few grams. 9.6 times 10 to the negative fourth grams of magnesium hydroxide. People get scared, but that, like, how do you even weigh that? Well, you don't weigh it on a scale that we have because our scales aren't that accurate. But you should expect a really small number. Why should we expect a really small number? Because if we go back to the original equation, our K value is tiny, tiny, which means very little of it is going to be turning into products. So that's part A. It's worth 2 points. The first point was calculating the solubility of magnesium hydroxide. That was your first point, that X. And then your second point was for the grams of the magnesium hydroxide. That's A. And then we're to part B. Part B says the energy required to separate the ions in magnesium hydroxide from its crystal lattice into individual ions is shown below, as is the strontium hydroxide. It says strontium hydroxide's lattice energy, the energy it takes to rip those things apart, is less. Explain why in terms of Coulomb's law. And so there's a couple things you got to point out. The beauty is they have the same charges here. So I'm not addressing charges, I'm addressing sizes of magnesium versus strontium. Good? And so magnesium, is it bigger or smaller than strontium? The magnesium ion is smaller. Why? Because it has less energy levels of electrons. That's your first point. You get a point for the comparison of the size of magnesium to the size of strontium. Good. And then the second piece of that is because, let's see how it says it. Explain why in terms of periodic properties, that's that part, and Coulomb's law. Coulomb's law, and I write Coulomb's law, energy is proportional to charges Q1, Q2 over the radius. Coulomb's law states that the lattice energy is greater for smaller radii. That's what I put. They put it's for indicating that a smaller inner ionic distance leads to greater lattice energy. That's the second point of that thing. That's your 4 points there on 2017 number 6. Have a great Good Friday and Easter weekend. See y'all soon, hopefully.